All right, here, welcome to the second video. Now we're going to be looking at kinetics. And so while we've looked at equilibrium previously, what we haven't really looked at is how long it takes to get to equilibrium, or really anything about how long a reaction takes at all. That is what the study of kinetics is for, because some reactions may happen in the blink of an eye, while other reactions may happen over the course of years or millions of years or even longer. And how we can study these is a key thing to understanding chemistry. And you've probably seen this in many different types of chemical reactions already, right? Whether it's, a bike rusting over time, that's a lot slower than a fire burning, for example, right? The rate of a chemical reaction is of key interest to understanding chemistry a bit better. This is the study of kinetics, and it is mathematically a little bit different than the stuff you've done so far, so definitely be prepared for that and watch those parts of the video carefully. Okay, with that, we'll go ahead and jump into the video. As we begin our study of kinetics, remember kinetics is about the rate at which a reaction occurs. In other words, how fast is this reaction going, or how long is it going to take for this reaction to complete? And there are many factors that affect kinetics, such as how much reactant is present. If there's more reactant present, more materials for that reaction, it's generally going to be proceeding at a faster rate as well. The temperature matters, and also the surface area of participating solids. And keep in mind that we actually know kinetics pretty well from a real-world perspective already. Some reactions happen really quickly, like a wildfire burning can potentially happen really quickly. And the more fire there is, the quicker the fire is able to spread. Washing hands is another great example. We're supposed to wait 20 seconds. That's because of the kinetics of that reaction, where we want to make sure that we're sanitizing things properly. And other reactions, like the tarnishing of a statue, could take years and years or tens of years to really complete itself. This is just to show that different reactions have really very different reaction rates. Again, if we want to increase the reaction rate, there are many things we can do, but this is a great example of how surface area speeds the reaction rate. In other words, if we have this iron nail that's all one piece, there's really not very much for the reaction to occur on, because the reaction is going to need to occur on the interface between the liquid and this metal. However, if we instead had iron filings or iron dust, then the reaction is going to occur much more quickly. And we can see this in the left image by the fact that there's just a lot more bubbles that are occurring, which is indicative of this reaction proceeding forward. More surface area, faster reaction rate, and this should kind of make sense, right? It makes sense that the more available iron surface there is, the faster the reaction will go. So keep in mind, this is just one way to increase the rate of a reaction. Okay, but how do we study kinetics on paper, right? How do we study it based on reactions? And let's take a reaction here. So this is hydrogen peroxide that's decomposing into 2H2O and O2. This reaction will occur slowly over time. Now, if we want to track the rate of this reaction, we can say, well, what is the rate of decomposition of H2O2, right? Because the rate at which the hydrogen peroxide is decomposing, that's going to be related to the rate that the reaction is proceeding and the rate at which both the water is being formed and the O2 is being formed. So if we want to get this rate, we can say the following, where we have the concentration of the hydrogen peroxide at T2 minus the concentration at T1, so basically final minus initial in regards to the concentrations, and divide that by how long the time took. This is really just like calculating a rate like a miles per hour speed. If we are at time 1 10 miles away from home and at time 2 we're 20 miles away from home, then we've traveled 10 miles. That's like the change in how far we've gone, and that's what the numerator represents here. And then we want to divide that by how long it actually took to get there. So if during those 10 miles that we traveled, it took us 10 minutes, then we must be traveling 1 mile per minute or 60 miles per hour. This type of rate is the exact same thing that we're looking here for kinetics. Note that it is going to be negative because we want to calculate the rate in some sort of a forward-thinking convention, like how fast is the reaction moving forward, almost as if we're calculating the arrow. And yet, if what we know most about is the reactants, they're going to be decreasing over time. We can call this the change in the hydrogen peroxide concentration over the change in time. Now, again, the minus sign is needed here because this expression is for decomposition, and we want to calculate the rate as far as how much is moving forward, right? And this delta here, this is change, final minus initial, and this should be something that we're relatively used to already. And if not, just keep in mind that this capital delta is a universal convention in science, which means final minus initial. What we're looking at here is the change in hydrogen peroxide concentration over change in time. But note that this isn't going to be the final understanding we have of kinetics, because we are going to get a bit more fine-grained, and we're not going to be confined to some specific time interval, like the fact that this may have taken place over 10 minutes, like I described a little bit earlier. Concentration is what we're really going to look at when studying kinetics. It's possible to use other parameters like the partial pressure of a substance if it's a gas when studying kinetics, but for this frame of reference, we're just going to use molar concentration. Okay, so let's think about these related reaction rates, right? If we have a reaction and we say, well, for this hypothetical reaction, we're moving forward at 0.1 molarity per second, right? And so this is the arrow. This is to say that 0.1 molarity per second of this reaction is occurring. And so this relates to the reactants being consumed and the products being formed. So go ahead and pause the video here and try to think about this, right? If the reaction is moving forward at 1 molarity per second, what are the rate of change of B, C, and A? And also think about this like, if I am going to be disassembling bicycles, well, maybe I can disassemble 1 bike per hour. Let's say we're not doing it very fast, but for the sake of easy numbers, if I can take apart 1 bike per hour, well, that means that 1 bike is going to be disappearing from my shop, and 2 wheels are going to be appearing as I take apart that bike as well. And when I say that I'm taking apart 1 bike per hour, what I'm really looking at is like the arrow in this recipe. So go ahead and pause the video and see if you can come up with these. All right, hopefully you've been able to give it an attempt. Remember that we're looking at the progress moving forward. So how many reactions are occurring? It's 0.1 molarity per second. And if the reaction is occurring forward at a rate of 0.1 molarity per second, this means that the rate of change of A is going to be negative 0.1 molarity per second because A is disappearing. And it's going to be disappearing at the rate at which the reaction is proceeding because A has a coefficient of 1 in this balanced chemical reaction. Therefore, what's the rate of change of B? Well, it's going to be negative 0.2 molarity per second because as we have 1 mole of reaction that moves forward, it's going to consume 2 moles of B. So the rate of change of B is going to be negative 0.2 molarity per second. And finally, what's the rate of change of C? Well, this is going to be positive 0.1 molarity per second because C is being created in this reaction and it has a coefficient of 1 in the balanced chemical reaction. Okay, so that's just sort of getting us started and realizing that the different components of this are all related. And really, as we look forward and we look at the rate law, what we're going to be focusing on is the reactants because they're the ones that are really going to determine the reaction rate and how fast it's going to be able to move forward. And keep in mind that this rate is not going to be constant. You know, if we have a large amount of H2O2 like we mentioned, the reaction may move pretty quickly at first, but as the amount of H2O2 dwindles, the reaction rate will likely slow as well. So if we have this, we can express the reaction rate as the following, where we say that the rate is equal to K times the molar concentration of H2O2. And mathematically, this gets at just what I was saying, that if we have a large amount of H2O2, the reaction will move forward at a greater rate. If that amount dwindles, there just won't be as much H2O2 that's available to proceed forward in the reaction, and the rate will decrease as well. K here is the rate constant. And remember before, what we talked about is that some reactions move really quickly on the span of seconds, and other reactions move very slowly on the span of years, or tens of years, or hundreds or thousands of years. K is what's going to determine that magnitude of the rate of the reaction. One thing to keep in mind here is that there's an exponent that goes here, and this is going to be really very important. And in this case, that exponent is going to be 1. This is K times H2O2 raised to the first power, or just K times H2O2, just to say that we're not raising it by any exponent, but it will be important to stay aware of the fact that we have exponents that are going to appear in the rate law, and that's going to be a fundamentally important thing for determining the kinetic behavior. Again, this is going to tell us the order of the reaction, and we'll discuss that very shortly here. And for here, that is going to be order of 1. Okay, so within the idea of the order of the rate law, there are many factors that determine the fundamental kinetics, and the order is one of these. And what is really behind the fact that different reactions have different orders, which we'll show mathematically here in a bit, is do we perhaps have one component breaking down into two? Or are two components colliding to create a third? Because in the first case, all that really matters is that first component. That component is breaking down into other pieces. Alternatively, if we have two components that are colliding to make something new, we need to have both of those components be present and collide with each other at the same time, and therefore the rate is going to depend on how much of each of those are present. Another thing that matters is that when we look at our net reaction, we often have hidden within that the fact that it could be a multi-step process, that a reaction could have a fast step and a slow step that doesn't exactly mirror the net reaction exactly. For this reason, some things that are part of the fast step of the kinetics may not appear in the rate law in a way that you would expect because their concentration doesn't limit the rate of the reaction. So again, here are three different examples of rate laws. In the first case, this is the one we just looked at. This is a first order reaction. And the mathematical implication here is that if the concentration of H2O2 is going to double, the rate is going to double because it's related to the rate in a 1-to-1 ratio, right? There's no exponent that's going to cause a different change. In this second example, we have what we'll call a second order reaction, and this is most likely what occurs when we need two of these particles to collide with each other in order for the reaction to move forward, right? From a microscopic perspective, reactions do have to have some way that the molecules combine in order to proceed forward with the reaction. Mathematically speaking, if the concentration of this C4H6 is to double, the rate is going to quadruple because the effect of the rate based on the concentration, the effect on the rate of the concentration changing is going to be squared. So if we double the concentration of C4H6, that will double the concentration, doubling squared, makes a 4 times factor on the rate. And the reverse is true also. If we are to halve the reaction, the rate would be quartered. And finally, we can have multiple different species here. So in this particular reaction, this is H plus and OH coming together to form water. It's first order with respect to each of these because for them to come together, we need an H plus and an OH. If either of them doubles, the rate will double. If both double, again, we have that quadrupling as this is going to be second order overall with each one of those species first order. Okay, so here's a question for you. If we change the concentration of reactant A in this chemical reaction from 0.1 molar to 3 molar, the reaction goes 3 times as fast. And we want to determine, well, what's the order of this reaction? And let's think back to our overall orders, right? That when we had first order, that said that whatever change we make to the concentration will be reflected in the rate equivalently. When we had second order, there was that squaring effect. So if we doubled the concentration of the reactant, it would quadruple the rate. So take a look at this one, pause the video, see if you can log an answer, and we'll discuss. All right, hopefully you've had some time to put down an answer. It would indeed be first order because what we see here is that the concentration is going from 1 molar to 3 molar, so a tripling. And what we see when we triple the concentration of A is the reaction rate also triples. Therefore, the relationship between the rate and the concentration of A is that 1-to-1 ratio. What happens to the concentration will be reflected in the rate, and we have a first order reaction. Okay, so here we have some data, and this is how we're going to see things most often because we're not always just going to say, well, you know, it triples, so what happens? Often that question comes from data. So basically we have 3 different trials that are present here. In the reaction, A goes to 2C. And in the first column, we have the data for trial 1. So we say, well, the concentration of A was 1.33 times 10 to the negative 2, and the rate was recorded below. Then we change the concentration to 2.66 times 10 to the negative 2 molarity, and the rate is recorded below, and we have another value for the concentration of A in the third column as well. So as we've discussed these orders, right, 0th order would mean that when the concentration of A changes, there is no change to the rate. So whatever we do to this particular species doesn't seem to affect the rate. That's what 0th order means. First order means that if we double the concentration of A, the rate would double. And second order means that if we double the rate of the concentration of A, the rate would quadruple. So what is this relationship between the concentration of A and the rate? Go ahead and determine that relationship and choose an answer here. And as a follow-up, if you can, what is the actual rate constant? And challenge yourself to do that one. We'll discuss that as well. So go ahead and pause the video and see if you can come up with a solution. All right, this is a bit of a tricky one, but what we've seen here is that if we take the first trial versus the second trial, the concentration of A is doubling. And then we want to say, well, what's happening to the rate? And the rate is actually quadrupling. So in this case, a doubling of the concentration has a 4x effect on the rate, and therefore it's a second order reaction. And we can see this in the other trials as well. We can go from the first trial to the last trial, and we see that the concentration of A is multiplying by 3, and the rate is actually multiplying by 9. And we can get these factors by taking the larger number and dividing it by the smaller number, and it'll tell you that factor by which it changes. So that's how we determine the reaction order based off of this rate data. How do we calculate the rate constant? And in this case, if we've calculated the order properly, we actually can use any of these to simply plug into our rate law, as we now have a proper rate law expression in terms of being second order, first order, or 0th order. So we can just plug in the value for rate and the value for the concentration of A and calculate the rate constant. Note that the units are going to depend on the units for rate as well as the units for A. So in this case, because it's second order, K is going to come out with the following units, which basically means that if K is multiplied by molarity squared, we need to come up with a unit of molarity per hour, which is the rate. Note that this per time unit, the fact that it's hours to the -1, inverse hours, is based on the rate that's given in terms of per hour. If we were given a speed, for example, in terms of meters per second, then things we would calculate would be based on seconds. And if it was meters per hour, then that would be a very different order of magnitude compared to meters per second. Okay, so this is an introduction to kinetics. I hope it has clarified some of the different studies that we're doing in this chapter, and I look forward to discussing more in the next video.